I haven't gotten up this early in some time for some various reasons. All right, so today I want to tell you about some work that we've been doing recently to benchmark the performance of the surrogate reaction method to constrain properties of neutron-induced reactions. And I particularly want to talk about this as it relates to the exciting era of accelerators like FRIB, which we are entering soon. Okay, so this is the challenge with which we're faced. This is the chart of the nuclei, and you can see the number of protons, the number of neutrons, the nuclei that have that are stable or functionally stable are indicated by the black dots. All the nuclei whose masses we knew in 2016 are in this dark shaded gray area, and all the nuclei that we think have a bound ground state are indicated in this lighter gray shaded area. And then these other colored lines indicate the astrophysical processes in which we believe these nuclei are made. And there are a lot of them. And what is important for the purposes of this discussion is that in many of them, neutron capture plays a role. And in particular, about half of these nuclei, heavier than iron, are made in the rapid neutron capture process, which is, as everybody knows, driven by the rapid capture of neutrons and then the subsequent beta decay of these neutron-rich elements to more proton-rich things that subsequently capture more neutrons and synthesize heavy things that way. So here's again, and the black dots are the stable nuclei, and this gray shaded area is the trajectory of a cold R process at the point of the problem when all of the free neutrons have been exhausted. So these are the most exotic things that you would make in this particular R process. These then blue squares are the nuclei for which we believe we know neutron capture rates. So these are, in case anybody's interested, these are Maxwellian average cross sections of 30 keV from Cabanis. And what I want to call your attention to here is that they're all along stability. And none of these things that we know are out along this R process path. And indeed, the R process path is very far away from the neutron capture rates that we know. And you could start to think that the picture is fairly grim, and we will never be able to constrain neutron capture rates that matter for these astrophysical processes, particularly the ones that run along these fairly exotic nuclei. But that's not quite the case. So recently, people have been doing large-scale sensitivity studies where they vary many pieces of nuclear data to see which pieces of nuclear data most strongly impact the final R process abundance pattern. So you can see that down here in this inset. And this particular sensitivity study by Matt Mumpower and collaborators looked at many different scenarios in which neutron capture rates could affect the final R process abundance pattern. What I've done here is to take the maximum sensitivity for each of the astrophysical scenarios that they looked at, and then showed you the most important things here. So the most important things, the things that you would measure, could you measure things, are in red, and the black squares are things that probably they would be a lower priority for measuring. And what's significant here is that many of the neutron capture rates that are of interest to the final R process abundance pattern are fairly close to stability. So here you can start to think about doing measurements that would allow you to constrain these neutron capture rates. So not all neutron capture rates are important, but we still have to come up with a way to measure them. And we should, guided by sensitivity, measure the neutron capture rates that are interesting. But we're still faced with the problem because we can't measure neutron capture on unstable nuclei. And the reason we can't do that is that typically the nuclei for which we're interested in the neutron capture cross sections are too unstable to make into targets. So we can't make direct measurements. We can't make direct measurements in normal kinematics. We can't make direct measurements in inverse kinematics either, because we don't have neutron targets. Seems obvious. So we need to come up with some way to indirectly constrain these cross sections. And the way that we have developed to do this is called the surrogate reactions method. So this is a method that was invented in the 70s to constrain properties of neutron-induced fission reactions. And recently, in the last 20 years or so, it has been developed to constrain the properties of other neutron-induced reactions. And the way this works is, so schematically, here it is. You've got a desired reaction. It's a neutron incident on a target. This forms a compound nucleus, and that compound nucleus decays through some channel. And you can describe that as the sum over all spins and parities of the product of the formation cross-section for this compound nucleus and then the branching ratio for its decay. And this is the desired reaction. For technical reasons, you can't measure it. So what one does is to come up with a surrogate reaction. So you take a different target and a different probe that is experimentally easier to measure, but forms the same compound nucleus, and then you select the same decay channel to measure in your experiment. And the probability for achieving this reaction is this formation probability for this compound nucleus, which we can call the entry spin distribution of the compound nucleus, and then the same branching ratio from it for its decay. And if you're talking about how easy this thing is to do, well, calculating this formation cross-section is pretty easy. You just need a reasonable optical model. Talking about the formation probability for the compound nucleus is more difficult because you really need to understand the reaction mechanism and the entry spin distribution and how they differ between your surrogate reaction and your desired reaction. And then describing how the compound nucleus decays is also difficult because you need to understand things about the nuclear structure of the nucleus that you typically don't. So my colleague Gregory Patel, who I'm sure many of you know, worked to develop the formalism for describing the entry spin distribution for the reaction mechanism that I'll spend most of my time talking about, and then the decay of the compound nucleus and the how one then puts everything together to extract the cross-section. This is machinery and work that was led by Jutta Escher. Okay, so we wanted to benchmark the performance of the surrogate reaction method to extract neutron capture cross-sections. And to do that, you first need to select a reaction. We selected DP because, like neutron capture, it drops off a neutron in the target. And then you need to select a target. And our requirements for the target were as follows. We wanted something that's stable, because those things are just much easier to deal with. We wanted to understand the structure very well. We wanted the product of the neutron capture reaction to produce an even nucleus, which has a strong 2 to 0 collecting transition, because that really simplifies the analysis of the situation. And finally, we're doing a benchmark, so we need to know the answer. So we need to have a case where the neutron capture cross-section as a function of the neutron energy was known. And for these reasons and others, we selected molybdenum-96. You can see the low-lying level scheme over here. Then we still need to do some theoretical work to develop this and understand what's going on. We need to understand the reaction mechanism really well, and we need to understand the entry spin distribution and how it's different from that induced by neutron capture. So this is a slide that I borrowed from my colleague Jutta Escher. The top, I like this because at the top it explains deuteron-induced reactions as, or DP, as an experimentalist understands it. So it's a very simple picture. You've got a deuteron coming in, the neutron is dropped off in the nucleus, and the proton comes out, and you measure the proton. But then down here, you have this broken out into how theorists understand the picture, and it's much more complex. So the theoretical description of this that Gregory Patel worked on is based on earlier work by these people, and it's similar to work that other people in the field were doing at the same time. People started to realize that DP is an attractive candidate for a surrogate reaction, so a lot of people simultaneously started working on to describe the reaction mechanism. And Gregory's model takes advantage of the fact that the deuteron is fairly weakly bound. So when it comes into a potential, it'll break up most of the time. And then you can have a number of different channels for what will happen. So first is breakup, elastic and inelastic. So the deuteron comes in, breaks up, the target is excited or it's not. And then you have complete fusion and evaporation. So the deuteron comes in, breaks up or doesn't. The proton and the neutron or the deuteron are absorbed by the target, and then a proton is evaporated. And then there's the channel that we're interested in. The deuteron comes in, it breaks up, the neutron is absorbed, and the proton zips off, and you measure it. So Gregory's formalism describes the entire cross-section and allows the breakup and partial fusion channel in which we're interested to be pulled out and then decomposed into a function of angular momentum. And if you look at the way the compound nuclear formation cross-section looks for the molybdenum-95 DP reaction, this is what you see. So this is the differential cross-section as a function of energy. This dotted vertical line is the neutron separation energy in molybdenum-96. And then you can see the cross-section broken down into various components. So you have the total cross-section, the total elastic breakup where the target isn't excited, and then the non-elastic breakup where the target is. You can also use this formalism to describe the formation probability for the entry spin distribution. So that's this quantity here and the equation that I showed you earlier. I'm going to show you a little movie here. Over on the left-hand panel, you see the individual contributions to this entry spin distribution, and over on the right, you see the cumulative side, or the sum of all of these distributions. This vertical dotted line again is the neutron separation energy, and the shaded area is the region in which we're interested. So, and over on the right, you'll also see a little label that has the spin and parity of that particular level. So negative parity states are dashed and positive parity states are solid. So this is how it looks. First, you get the 3 minus, 4 minus, 2 minus, 5 minus, 6 minus, and then you start getting positive parity states, and they're concave up rather than concave down. So using this formalism, you can understand the entry spin distribution for the compound nucleus. So this is a significant thing, and as you will see, it matters a lot. So now that we have these theoretical tools in hand, we can do the measurement. Although, of course, in reality, these things were developed in parallel. We did this measurement in normal kinematics at Texas A&M University in College Station, Texas, with the Starlighter array. This is an array of silicon detectors and surrounded by up to six high purity germanium detectors. You can see a close-up photograph of this setup in the lower left-hand corner. So the beam is coming in from the left side of the page. It is impinged upon a target, and the target was a milligram per square centimeter thick enriched molybdenum-95. The beam was about 12.4 MeV, a deuteron beam at about 0.3 nanoamps provided by the cyclotron at Texas A&M University. After the particles hit the beam, most of the protons go downstream and are detected in the silicon detector telescope. You can see a photograph of one of the silicon detector telescopes up here. And you're looking at the backside here, so it's segmented into, I believe, 16 strips, and they're segmented into 16 channels on the backside, and they're ganged together into 8. And on the front side, they're segmented into 48 rings, and they're ganged together into pairs of 2. So you read out 24 channels on the front side, 8 channels on the back side, and you get azimuthal and angular position from this. Then this is surrounded by up to 6, but in our case 4 compton suppressed high purity germanium detectors, and you can see a photo of that down here. And what we're doing with this detector is constraining this quantity. So this is the quantity, this is the probability for making the reaction in our surrogate reaction. We're going to calculate the probability, the formation cross-section for the compound nucleus in the desired reaction. We're calculating the entry spin distribution for the surrogate reaction using Gregory's formalism. And then we're constraining the branching ratios by measuring this probability, which is the same as this calculated quantity. This probability we call the gamma ray emission probability. It is, and it's the coincidences between the number of protons and the number of gamma rays is a function of excitation energy divided by the number of proton singles as a function of excitation energy. We're going to fit this quantity and then use the resulting constrained Hauser-Feshbach parameters to calculate the desired cross-section. And over the next couple of slides, I'm going to walk through in detail how we do that. So our particle gamma detector allows us to measure particles and gamma rays in coincidence. If we look at the gamma ray energy in coincidence with the reconstructed excitation energy that we get from looking at the kinematics and measuring the proton, you get a matrix that looks like this. So you see the neutron separation energy is here. Below the neutron separation energy, you see states that are populated in molybdenum-96, and above the neutron separation energy, you see states populated in molybdenum-95. So this is just a cartoon of what's happening. Below the neutron separation energy, you're doing DP to excited states in molybdenum-96, which then de-excite, and you see the characteristic gamma rays from this de-excitation. Above the neutron separation energy, you have competition between gamma ray and neutron emission. So you can see here, these are the first 2 excited states marked with the red asterisk and molybdenum-95. And you can see those start to turn on as you cross the threshold for them. So what one does in this experiment then is to bin up your excitation energy matrix into whatever resolution you think, whatever excitation energy resolution you think your experiment can support. In my case, this is about 100 keV. And then you project that down on the gamma ray energy axis, and then you fit those gamma spectra. Then you divide by the number of proton singles in that spectrum, which is really easy. You just count how many protons are in that bin, and you get the gamma ray emission probability as a function of excitation energy, as you see here. So this is these are for low-lying states in molybdenum-96. I measured about 30 transitions, and I'm showing you 5 of them here. But there was quite a lot of data for this, as you can see. So this black line is the first 2 to 0 transition. And then these are higher lying, mostly ERAS transitions. You'll notice that the first 4 to 2 is cut out, and that's because it's a doublet with the third 2 to 2. So analyzing that spectrum was a little more complicated, and as you'll see, we didn't need to do it. So just to remind you, we're measuring this quantity, we're going to calculate this quantity. The way that we do this, or the way that UTA does this, is to calculate this quantity a bunch of times and then minimize the difference between the calculated and the experimental gamma ray emission probabilities through a Bayesian Monte Carlo fit and minimizing this chi-square. If she does that over this fitting range, and this is the same shaded gray area as I identified to you earlier, you get these really nice fits. So you can see not only that the agreement between the fit and the data is quite good, but that the agreement extends far outside the fitting range. So this gives you a large number of Hauser-Feshbach parameters that are used to constrain the nuclear level density and the gamma strength function. And using these, you can calculate the desired cross-section, as you see here. Now, critically, and one of the things that I think is really attractive about this approach to constraining neutron-induced cross-sections is it doesn't require either D0 or gamma-gamma, and that's great because typically, for the cases in which you're interested, these quantities are not available. And other indirect methods do require these quantities. So this is how it works. So here's the cross-section as a function of neutron energy for molybdenum-96. You can see the data here that existed in the red and black dots. Here's the evaluated cross-section. So it goes through the black dots and the red dots where there is data. This is what evaluated cross-sections do. Outside of this, it depends on systematics. This is the Weisskopf-Ewing approximation. So the Weisskopf-Ewing approximation is an early approach to the surrogate method. What one does there is to say that the entry spin distribution doesn't matter, and the decay of the compound nucleus depends only on the excitation energy, not on the spins and parities. This works reasonably well for fission above an MeV or so, but it has been shown several times prior to this, and again in this case, that it is not adequate for neutron-induced cross-sections because the cross-section that you get from the Weisskopf-Ewing approximation does not agree with the data at all. However, if you take the approach that I've ascribed to you and consider rigorously the entry spin distribution induced by the surrogate reaction, as well as the constraining the decay of the compound nucleus in the way that I've demonstrated, you get a cross-section that agrees with the data very well. So that's shown here in the blue line. The shaded area is the uncertainty from the fit. So it's the experimental uncertainty. It doesn't include the uncertainty in the entry spin distribution. We're working on developing that. And I want to emphasize that this cross-section that we've extracted doesn't know anything about the evaluated cross-section. It doesn't know anything about the previously existing data here. It just knows about the entry spin distribution and then the systematics for the nuclear level density. And I would say that this works extremely well. So I would say that this conclusively demonstrates that one can use the surrogate reaction method to constrain neutron-induced reactions. And we've done this for other cases as well. So Jutta Escher and Jason Burke, who's an experimentalist at Livermore, showed that this works for pickup reactions as well, and that it works in much more complicated situations. So for odd-odd and odd-even systems. So they used the same experimental apparatus, and they did 2 surrogate measurements. As a benchmark, they did PD on zirconium-92, and the surrogate reaction of interest here is zirconium-90 in gamma, and you can see that result here. So here's the cross-section as a function of neutron energy. The data are shown In the red and purple dots, the sort of beige thing is the Tyndall evaluation, and then there are other evaluations in dashed lines. And then the cross-section extracted through this measurement is shown in the blue line, and the shaded area is the uncertainty. One reason this uncertainty is larger is because this includes a full treatment of the theoretical uncertainty induced by the entry spin distribution. So having demonstrated that this works, they did the first measurement on a radioactive target, and this was yttrium 89 PD for yttrium 87 neutron capture, and this is yttrium 87 is radioactive, so this is quite difficult. And these are the cross sections that they extracted from this. Then here are the evaluations, which of course are made in the absence of any data. This is a much more complicated case. It requires a two-step reaction mechanism because you're making a hole in the target, but the agreement with data is good. So I would say that between these two things, you can be pretty confident that the circuit reaction method can be used to extract neutron capture cross sections. It can also be used for the properties of things that are not neutron capture. So as I've said, it was developed to constrain neutron-induced fission cross sections. This is a slide that I borrowed from my colleague Richard Hughes, and you can see over here he's got the neutron-induced fission cross section as a function of neutron energy for plutonium-237. The red dots are the measurement, and the blue dashed line is the evaluation, which again is made in the absence of data. This can also be used to extract quantities that are not cross sections. So Chiba et al. Have used this to constrain fission fragment mass distributions from charged particle reaction for a host of different actinides. And my colleague Tomi Adekendele, who is now a postdoc at Livermore, has used this to constrain the fission multiplicity from neutron-induced fission on plutonium-231. So here's nu bar as a function of the equivalent neutron energy. You can do a lot of things with the surrogate reaction method. But thus far, these measurements have all been in normal kinematics, and we want to extend this to inverse kinematics for exotic nuclei. Just to remind you, in inverse kinematics, you've got a radioactive beam incident on a CD2 target, which is essentially a plastic shopping bag. The proton's coming out at back angles, you're measuring it in your silicon detector. The beam-like recoil is going downstream, and you're measuring that in a recoil detector. So the detectors that you use for this sort of thing, they need to be very big. They need to have most of the solid angle covered by silicon, and they need to be surrounded by as big a germanium detector as you can find. And in the States, that means you want to use Gamasphere or Cortina. So we did this when I was a postdoc at Rutgers University working at Oak Ridge. We put Goddess, we developed Goddess. Goddess is an array. It stands for Gamasphere Aruba Dual Detectors for Experimental Structure Studies. The future is not part of this acronym, but I really like this Back to the Future logo, so I'm going to continue to use it. So down here, you can see a picture of Aruba. Aruba is an array of silicon strip detectors. It's strictly speaking just the barrel. The silicon strip, there are two types of silicon detectors. There are delta E detectors, which are quite thin. And then there are the Super X3 detectors, which are thicker. They are segmented on the front side into 4 resistive strips, so you can get position information with the resolution of about 1 millimeter by dividing the charge across the strip. And on the back side, they're segmented into 4 pads, so you can get, which are perpendicular to the strips. This is augmented by an array of annular detectors. You can see a photograph of them here. I'm not sure if you can really see it, but they're segmented with a variable pitch on the front side. There are 32 channels, and they're segmented such that you get a degree of angular resolution from these. And the signals are brought off on these capped-on cables, which you can't really see, but allow us to maximize the coverage of silicon here. And they're segmented on the backside into 4 wedges. So we put this inside of Gamasphere over here. You can see the beam pipe is coming in to the page. The target would be coming in from here up top. And then all of the signals are routed through this bell-shaped container that we call a flower pot. And they're brought up through this mess of cables to our data acquisition system. We also put this inside of Cortina. So we fielded this twice thus far. You can see the over here in the lower left-hand corner, you can see the target ladder that I identified earlier. This is inside of Retina. You can see a better view of our preamps, which are cooled by these computer fans, and then all of our signal cables running over the top of the FMI. Here's a close-up of the scattering chamber inside of Gratina. Gratina almost shuts, but not quite, because the scattering of the area available for a scattering chamber inside of Gratina is a little smaller than the area inside of Gammasphere. So we're redesigning this ball so that it will fit. So we've run this twice thus far, and there are a number of papers, and I realized that I don't have any slides with any data from Goddess in this talk, so I apologize for that. But in the future, we're going to field it to do a number of measurements, including this very challenging measurement using barium-143. So this will be a caribou measurement at Atlas. The motivation here is for stewardship. So the 144 mass chain is used to interpret nuclear test results, and we're interested in reactions that create or destroy nuclei in this chain. So this snapshot of the chart of the nucleides I'm showing you is independent fission product yields from fission spectrum neutrons and uranium-235. And this is color coded according to the yield. So the more green something is, the more it's produced. Barium-143 and 144 are highly produced in this particular reaction. And so we're interested in doing barium-143 and gamma to constrain the neutron capture cross-section. Barium-143 is also is predicted to be the most intense thing that comes out of the caribou source in a reaccelerated beam, so it's an attractive candidate for this reason as well. We submitted this proposal to the Atlas PAC, and they approved the measurement, so one day when we're allowed to do measurements again, we'll run it. My colleague Richard Hughes also got wind of a measurement that had been done with Shark at Triumph for nuclear structure by Stefan Cruz and Peter Bender. So they did strontium-93 dp gamma, and they were kind enough to give Richard the data so that he could do a surrogate analysis on it. It's interesting for the R process and also to interpret nuclear test results. So this is data from strontium-94 dp. Sorry, this is strontium-95 dp, I believe. Yeah. So here are the low-lying. Here's the 2 to 0 in this nucleus. The data is a little bit worse quality than the one I showed you before, but that's because the statistics are lower. They ran a radioactive ion beam for about a day and a half, I think, and I ran my experiment for 5 days. So the statistics are a little bit different. But still, the gamma ray emission probabilities look similar, and Richard is working to constrain the cross-section for N gamma here. He's also proposed a follow-on measurement for strontium-93 dp, which is interesting for the R process, and the Triumph PAC has approved that measurement. So again, when we're able to run experiments again, we'll do this measurement. So I'm going to wrap up the experimental part of this talk and now give you some prospects for the future. So I hope that I've convinced you that these surrogate measurements are robust, but the limitation, if there is one, is that they are reaction-based measurements, so they require fairly high beam rates. However, they don't require auxiliary information like the average S-wave spacings, the D0 or the gamma-gamma. The unstable beams that we're interested in produced at the necessary rates, so around 10 to the 5 particles per second, are beyond the reach of many current facilities, but the FRIB era will be an exciting time for these measurements. Now, and there are 2 options in the FRIB era. So you can do a fast beam measurement, and that's attractive because the rates are higher, but it's also quite challenging because as you increase the beam energy, the cross-section for transfer reaction drops. So you need to at least degrade the beam energy. Producing heavy things, so things heavier than about mass 100 in fragmentation, and then degrading the beam means that you will have a very messy charge state distribution. So it will be quite a challenge to identify the isotope of interest in the fragmentation soup. But other people will have this problem as well. So I'm confident that progress will be made, and that one day this will be a possibility. FRIB will also have on offer the reaccelerator, RIA, and that's very attractive because it's at energies where these cross sections are reasonably high, and because you're rethermalizing the beam, the charge state problem won't be bad. You'll be able to unambiguously identify the thing that you're interested in. So these are prospects for that. So here are the beam rates for reaccelerated beams from full FRIB. This is the 400 kilowatt machine. And this is obviously a prediction. Here are the stable nuclei and the neutron capture rates that we know. Here's that Koldar process path. Here's the sensitivity study from maximum power. And remember, the red things are more interesting than the black things. And this black envelope here that I've drawn is the 10 to the 5 particle per second rate. And if you're looking at fast beams, then beam rates are 1 to 2 orders of magnitude more. And this envelope goes out a couple units farther away from stability. Now I've added 2 things to this plot. There are these yellow circles, and these yellow circles are nuclei for which the DPQ values are sufficiently high that the protons at back angles where your cross sections are maximized are coming from a state, an MeV above the neutron separation energy at least an MeV, so they're above threshold in your silicon detector, and you can do these measurements. So quite a number of these things have these have reasonably high Q values, and you can measure surrogate reactions on them. This yellow dash line is, I thought I would goof off and add it. This is the fission fragment distribution from a californium-252 source. So this is what you could get out of Caribou. If you could, and that means you would, if you could get everything out of Caribou at 10 to the 5 particles per second, which you currently can't. And when I say that, I mean that you currently can't get anything out of Caribou in a reaccelerated beam at 10 to the 5 particles per second. But as you probably know, they're changing the situation at Caribou. So instead of being a spontaneously fission source, they'll put a neutron driver on it, and that will increase the beam rate, the available beam rates. So if they did that, or when they do that, and if it improves the situation substantially, you will be able to do some things with Caribou that are of interest to the R process, which you can't touch with RIA. And I think that's a really exciting prospect. So I want to wrap up. This is the opportunity we're presented with. So here's that plot I showed you in the beginning with the nuclei that we know, the nuclei we think exist, the schematic trajectories of these processes. The black envelope is everything that will be able to produce beam rates at sufficiently high rates to do surrogate measurements on, and this yellow envelope is what one could do with Caribou. So it's a very exciting time for these measurements. I look forward to doing lots of them. I also look forward to your questions. I'd like to thank my collaborators and you for your attention.